Okay, so I want to introduce to you the concept of work and energy. And the first thing we need to do is define the word work, because it's not going to be used in our traditional sense of the word, as in I'm working to make money. It's going to be used in the physics sense. So, work is defined as the force exerted on a system that causes displacement. And it's going to circle around the equation W equals F times D. So work equals force times distance. And this works with this definition, in that it's a force exerted over some displacement. So how far an object travels, the distance. So work equals force times distance. And work is going to be measured in joules. So it is measured in joules. One joule is equal to 1 Newton meter. So if you think about it, force is measured in newtons, distance is measured in meters. So the joule equals Newton meters. So it's kind of a logical progression of units. So work can be done in just one direction, like you're pushing it left, you're pushing it right. But it can also be done at an angle. So if you're pushing, let's say, a box, and you're pushing it this way, the force being applied to the box is on an angle. So you would just modify the equation to also have cosine and sine. So we're sort of getting back into trigonometry a little bit with this next unit, and hopefully you remember a lot of that from when we were talking about forces. So let's go over some practice problems with work, just so that we become familiar with what these questions are going to be asking us throughout this unit. All of this can be found in Chapter 10 of your textbook. If you want to follow along in there, I'm on page 268, and we're doing example problem number 1. And that basically reads, a hockey player uses a stick to exert a constant 4.5 Newton force forward to a 105-gram puck sliding on ice. So you have ice and a little hockey puck thing here. Now it tells you the weight, and we know that if we were to draw a free body diagram of this, we would have the weight force going down and a normal force going up, and we've just established that there's another force pushing it that way, and it's a constant force of 4.5 newtons. So we know this is 4.5 newtons. We know that the weight force of the puck, because it's 105 grams, we have to change that into kilograms. So let's see, 105 grams. Kilograms is 3, so kilo is 1,000. So you're moving the decimal place over. 3 spots. So you actually have 0.105 kilograms. And if you recall from the previous chapter on forces, in order to find the weight force, you take the mass and you multiply it by 10. So you're actually going to get 1.05 newtons going down. Now, because the puck is obviously not floating on this ice, you're going to have the same force going up. So that is our basic free body diagram, and it's on ice because it's a frictionless surface. So we don't have to worry about any force opposing this motion. So we have all of the information we need to complete the problem now, because we want to know okay, so let's refer back to the problem. The problem says a hockey player uses a stick to exert a constant 4.5 Newton force forward and to a 105 gram puck sliding on ice over a displacement of 0.15 meters forward. How much work does the stick do on the puck? So it's asking for work. So the only thing we're missing on the board right now is distance. And we know that this puck is going to travel 0.15 meters. So all we have to do now is plug it into the work equation. As I talked about earlier, our work equation is work equals force times distance. Our distance is 0.15. Our force is 4.5. So then our work comes out to be 0.675 joules. So far, the problems have been pretty simple. So let's take an example and sort of take it to the next level, because right here, the puck was moving in a straight line. So it was really easy. We didn't have to deal with any messy angles or something. But in our next problem, we're going to have to factor that in. So the example problem is, or reads, I should say, a sailor pulls a boat a distance of 30 meters along a dock using a rope that makes a 25-degree angle with the horizontal. How much work does the rope do on the boat if the tension is 225 newtons? So first, let's write down what we know. We know that force equals 225 newtons. We know that the distance is going to be 30 meters, so D equals 30 meters. But we have something else to factor in, because if it was just pulling the boat 30 meters straight, we're done. We have all that we need. But we have to factor in the angle, and the angle is 25 degrees. So if we were to draw a picture of this, you would have a boat being pulled at a 25-degree angle. So all we have to do is factor in the distance. And the way that we do that is we are going to use these numbers. It's going to be work equals force times distance. And we are going to sort of add this part onto the equation. And it's going to be times cosine of the angle. So when we go to plug in our numbers, it's going to be 225 newtons times 30 meters times the cosine of 25. And that is going to equal our work. So we've really only added one component to it, and that is the cosine. And if you multiply all that together, you would get 6.93 times 10 to the third I believe. And that is going to be in joules, because work is always measured in joules. Okay, and that sort of wraps up what you need to know about the work equation. It sort of ties in your previous knowledge of forces, and then it bridges the gap into energy, which is going to be the main focus of our next unit.